Hi, everyone. Welcome back. We have our final talk for the morning in the contributed talks, and it will be by Prairie, Wentworth, Nice at Cornell University, speaking about Matroids representable over non-abelian groups. Take it away, Prairie.
Thanks, Mark, and thank you to the organizers for organizing such a wonderful conference this week. It's been a lot of fun. So today I'm going to tell you guys about matroids representable over non-abelian groups. So I'll start with the matroid, talk about what it means to represent it, and then we'll go to a new way of representing matroids by non-abelian groups. So matroids were first introduced by Whitney in 1935, and you may have seen them around in whatever you work on, even if you don't work in matroids in particular. They show up in a lot of fields. There are applications to topology, various things that end in the word geometry, lots of areas of combinatorics. So there's a whole wealth of applications, but I mostly study just the general structure of matroids, in particular matroids represented by groups, and a little bit of some coding theory, but I'm not going to talk about that today. So there's a whole number of ways you can define a matroid. I'm going to use this definition today. So this is the rank definition of a matroid, and we're going to say that a matroid on a finite set of elements, which I'm going to call E, is a function from the power set of E to the integers which satisfies these three properties. So this function is I'm going to call the rank function. I didn't put that word anywhere on the slide, but I'm going to use it a lot. So that's what I mean when I'm talking about a rank. And our rank function is subcardinal. So what that means is the rank of a set of elements can't be bigger than the cardinality of that set of elements. And we're also going to say that the rank is always non-negative. It can be zero, especially we'll always have the empty set, and that will always have rank 0. We're also, property 2, we're going to require that our rank function be monotonic. So smaller subsets have to have smaller ranks. And then the last property is the submodularity property, and that says that the union of two subsets, the rank of the union plus the rank of the intersection of those two subsets has to be less than or equal to the sum of the ranks of those two subsets. And that should look sort of similar to like properties of dimensions of vector spaces, maybe. So this is the definition I'm going to use today. So for one example, we can look at the set of just 3 elements. This is a special matroid. It's a special type of matroid called a uniform matroid. And we're going to look at one specific uniform matroid, U23. So U23 is the matroid I get when all of my subsets of size 2 or smaller have rank equal to their cardinality, and then everything bigger just has rank 2. So in this case, there's only one subset bigger. So in other words, all of my single elements have rank 1, all of my sets of 2 elements have rank 2, and then the set of all 3 elements has rank 2, and I didn't put it on here, but the empty set would have rank 0. And we can also think about U23 if we want as being the edges of this 3 cycle. In general, graphs are a really nice way to think about matroids. Not all matroids can be represented by graphs, but it's sort of the easiest way to visualize things. So I'll go through one more example. If we take the edges of any graph G, we can make a matroid out of it. And our rank is going to be the number of edges of a maximal forest in the subgraph induced by whatever set we're looking at. So if I look at this graph here, if I look at the first 3 edges, so edges 1, 2, and 3, and I want to know the rank of 1, 2, and 3, in order to get a tree or a forest, I need to remove at least one edge, because right now it's a cycle. So in this case, the rank is going to be 2. I can pick non-consecutive edges, like 1 and 5, and here there are no cycles at all. So this is going to have rank 2 as well. And this is also this particular graph is an example of a non-uniform matroid. I didn't put it on here, but if we looked at, say, the set 1, 4, 5, that would have rank 3. So that would be a 3-element set with a different size rank than the 3-element set listed there. So we say that a matroid is representable over a field, essentially if we can represent it by vectors with entries in those fields. So we want the rank of the span of those vectors to be the same as the rank of our matroid. So for the 2 examples I just showed you for U23, we can represent it in any field using this matrix. with 3 elements, if I look at, and I'm looking at the column vectors of these matrices in general. So if I look at any individual column that spans a rank 1 space, any pair of columns spans a rank 2 space, and all 3 of them is still rank 2. And for my 5-element graph, I get this slightly bigger matrix. This has 3 rows in it because my matroid has rank 3. I could put more rows in it, but I need at least 3 rows for this to have the correct rank. And these are both examples, because they're graphic matroids, they're also what are called regular matroids, which means they're representable over every field. And these are examples of matrices which will represent them over every field. But I should say, in that sense, these are badly chosen examples because this is not true in general. In fact, in general, if you picked a random matroid, it would not be, especially as the size of your matroid gets bigger, it wouldn't actually even be representable, let alone graphic. That being said, a lot of the ones we want to deal with are both representable and graphic because they're particularly nice. So another thing we look at are matroid minors. So a matroid is a minor of another matroid if we can get it by a series of operations called deletions and contractions. If you're familiar with graph theory, the idea of a matroid minor should be sort of similar to the idea of a minor of a graph. In fact, for graphic matroids, it's very, very much pretty much the same. So what are deletions and contractions? A deletion is what it sounds like. We're just taking out an element. And when we look at our new rank function, we're looking at just our old rank function, but restricted to our new set of elements, which is missing something. So I've listed the ranks of all of the 3-element subsets of this graph. And if I delete the edge 2, I just stop caring about any of the subsets that had a 2 in them, and my rank function otherwise doesn't change for my remaining sets. Contraction is what is the dual operation of deletion. So I'm managing to give a whole matroid talk without defining duals, which is pretty strange. So if you don't know what they are, don't worry about them, but they're a nice property of matroids that they have duals. And so one way you can think about contraction, if you're familiar with that, is it's the deletion in the dual. If you're not, you can think about it as we sort of delete the element, but in a different way. So in this case, if I want to contract on the edge 2, I think about the 2 vertices on either side of 2, and I want to squish them together into one vertex. So it's going to change what happens to my overall graph. My edge 1 just sort of loops over. And this means we now reduced to the same set of subsets we had when we deleted an element, but our rank function isn't quite right. So if I look at these 3 elements, 1, 4, 5, before they had rank 3, but now they should only have rank 2. And likewise, all of the 3-element subsets in this case should have rank 2. So these are how we can get our minors. We can do any combination of deletions and contractions in any order, whatever you want. And we can get various minors. And what's particularly nice about minors is that if a matroid is representable over some field, then every minor of that matroid is also representable over that field. And the converse of that tells us that if we have some matroid that's not representable over a field, then as soon as it's a minor of some other matroid, we know that that matroid can't be represented over that field. And so that's a very nice way, or a very useful theorem for helping us classify which matroids are representable by which fields. So in particular, if we're looking at one field, we can look at the class of excluded minors for that field. And we say that a matroid is an excluded minor if it's a minimal matroid, which is not representable over that field F. So if you're familiar with graph theory, if you have K5 or K33, then your graph isn't, as a minor, then your graph is not planar. That's the general idea we're thinking about here. And so there's been a lot of work in defining excluded minors for matroids over various fields. In 1958, Tutt showed that U24, which is a different uniform matroid, is the unique excluded minor for the class of binary matroids. And then in 1971, Rota made a conjecture that there's a finite list of excluded minors for the class of matroids representable by any finite field, which is a pretty big conjecture and has not yet there's no published proof of that as of right now. 8 years later, Seymour and Bixley showed that there was a finite list for ternary matroids, so matroids represented over a field 3 elements, and it took another 21 years for us to get to matroids on 4 element fields. And so those are both finite lists. There's no counterexample yet to this finite list conjecture, but we don't know where it's going. So that's some of what we've done in Matroid and sort of representations by fields. And so what I want to tell you a bit about today is a new way of representing matroids due to my advisor, Ed Schwartz, where we look at matroids represented by graphs or by groups. So if we take a finite group, I'm going to call my groups gamma, we can look at the direct product of gamma with itself n times. So I'm going to do an example. We can take something like Z3. I'm going to think of it as the additive group on 0, 1, and 2, and then take the direct product of it with itself 3 times, which is going to be the 27 elements. That's all the combinations of 0, 1, and 2. And I'm going to do addition on my new group component-wise. Then we can think about projections onto different coordinates of this group. So if we're looking at subsets of the coordinates 1, 2, and 3, we can look at the projection onto just the first coordinates or the second coordinates or the third coordinates and the group we get there. And in particular, we're going to want to look at these projections for when we have a subgroup of our group, of our direct product group. And this is how we're going to define our a specific rank function. So we're going to define a rank function on these subgroups of these direct products by taking log base the size of the group of the cardinality of the projection onto the group. And I'm going to do an example so we can see what's happening there. So this is a subgroup of the direct product of Z3 with itself 3 times. And if I want to look at just the first column, I want to know what's the rank of element 1. I want to look at the projection of this subgroup onto coordinate 1. And here I have 0, 1, and 2. So there are 3 elements in that subgroup. I don't care how many times they're repeated. I just care that there are 3 distinct ones. So my rank is going to be log base 3, since gamma is Z3, of 3, which is 1. If I look at the projection onto, say, the second and third columns here, the second and third coordinates, now I have 9 elements. So my rank of 2 and 3 is going to be log base 3 of 9, which is 2. And similarly, if I'm just looking at my whole subgroup, that's the rank of the whole subgroup is going to be log base 3 of 9 again. So it will also be 2. And so RH, this rank function in general, is what we call a subcardinal polymatroid. It's a function from the power set of our element set to the real numbers, which satisfies the 3 properties that we required of matroid rank functions. So it's the same definition as for a matroid, except now instead of requiring our function go to the integers, it actually goes to the real numbers. And so this generalizes the idea of representation over a field to representation over a group for this larger class of subcardinal polymatroids. But what I'm going to focus on today is just the implications for matroids. So you can ignore this particular definition if you want. And so we're going to say that a matroid is representable over a group gamma if there's some subgroup where the rank function of that subgroup gives us the rank function of our matroid. And as with fields, it turns out that a matroid is representable over a group gamma, then every minor of that matroid is also going to be represented over gamma. So again, this gives us a nice way to start trying to classify matroids representable by various groups. So as a quick example, if we look at this subgroup we had before, if I look at any of the individual coordinates, I'll always find rank 1. Any pairs of coordinates will give me rank 2. And we saw before that the whole thing will give me rank 2 as well. So this is a matroid, not just a subcardinal polymatroid, because all of my outputs are integers. And in fact, this is the matroid that we've looked at several times already. This is U23. So our first theorem turned out to be pretty nice. So it turns out the matroid U23, this one we've looked at, is representable over a group gamma exactly when gamma is abelian. So the idea of how this works, if gamma is abelian, we can actually just construct the subgroup whose rank function will give us the rank function of U23 by taking all of the pairs of elements in gamma as our first two coordinates and then subtracting them to get our third coordinate. And I won't prove it here, but this will give you the right rank function that you need. To go the other way is a little bit trickier, but let's say we have some gamma that represents U23, then we can consider a function from, say, think about going from like the first two columns of the first two coordinates of the elements in our subgroup to the third coordinate, where we say f of our first two coordinates exactly gives us the third coordinate. And then we're able to use this function to define two new functions, which take the group as both domain and codomain. And what we found with these two functions is that the images of these two functions commute. The image of A commutes with the image of B. And it turns out that both of their images is the entire group gamma, which means that all of the elements of gamma commute with all of the other elements of gamma. So gamma must be an abelian group. So that's the idea of what happened here. And this turns out to be particularly helpful in showing that U23 is the unique excluded minor for matroids represented by non-abelian groups. So the idea here is we can partition matroids into two groups. We can look at all of our matroids that have circuits of size 3 or bigger, and all of our matroids that don't have circuits that are that large. So a circuit, if you're not familiar with it, these are all of our sets where the rank is 1 less than the cardinality of the set. They're minimal dependent sets. If you like graph theory, these are the cycles in graphs. So the idea is if we have a circuit of 3 or more elements, we have U23 as a minor. So if I think about like a cycle on a graph, I can keep contracting around the cycle until it's a 3 cycle. And if I have that cycle amongst some other stuff happening in the graph, I can delete everything else. So all I'm left with is the 3 cycle. And that works in general. So U23 is always a minor of something like this. And it's not represented by non-abelian groups. So nothing that has such a circuit can be representable. And the other case is the case where we have no circuits of size 3. So everything's quite a bit smaller. And in this case, we can actually we can give a construction for how to construct a representation over any group gamma. And it turns out that all you need is to take a specific set of direct products of copies of gamma, copies of the diagonal subgroup, and the identity element of your group. And in general, the copies of gamma will correspond to independent elements in matroids, diagonal subgroups will correspond to parallel elements in a matroid, and the identity element will correspond to loops. And so this shows us that U23 is the unique excluded minor for matroids represented by non-abelian groups. So it completely classifies matroids over non-abelian groups. Unfortunately, abelian groups are not quite so simple, which isn't surprising given that fields themselves are not quite that simple. And we can look at fields as abelian groups as well. So we do know that regular matroids, so matroids representable over every field, are also representable over every cyclic group, but we don't have a lot beyond that. And that's where I'm going to stop. So thank you all very much.
Let's all thank our speaker. And we are now open for questions. Does anyone have questions for Prairie?
Can I ask something?
Mm-hmm.
Oh, yeah. So So for the original type of the representation, so I mean the representation over the field, I mean motivation is quite obvious, I think, because we can think the Matroid from the matrix. But I wonder that what is this type of background of this motivation of this type of representation of the Matroid.
Yeah, so this type of representation, it's related to the representation over fields in that you can think of it being related. Instead of looking at the column space of the matrix, we're looking at the row space of the matrix. So if I look at, this was my U23 example, if I look at these two elements, these are actually the rows of the matrix representation I gave you of U23 earlier, and they generate this subgroup they would generate a subgroup in any field that would represent U23. And so in general, this will give you like this will always give you the same, like looking at the row space will always, and this rank function will always give you the same rank function as looking at the columns.
So you mean that,
but this came out of other work that my advisor was doing, was actually how he like first came across it.
So when you consider this type of the representation, the support of these things are, I mean, support of these vectors are circuits or co-circuits. That's what you mean?
Can you say that one more time?
So you say this is related with the rows of the matrix representation.
Yes.
So you mean that, I think I remember that the support of each rows are correspond to the co-circuits. So also everything's represented by these vectors are exactly correspond to I mean, maybe more because you have much more things, but
yeah, there's a direct correspondence. There's more groups, and so you can represent more things, and you won't always get like integers, which is why sometimes these groups will represent like the subcardinal polymatroids. But anyone that represents a matroid, you can give a corresponding matrix if it's like a subgroup, if the group also happens to be a field.
can I ask one more?
Sure.
So if we have two groups, so then, I mean, if we have group G1 and G2, then if one matroid is representable over G1, then can you guarantee that it is representable over G2 if there is a group morphism from G1 to G2?
So the answer to that is sometimes. So for instance, if I have something that's represented over like Z mod NZ or like Zn, then it's always representable over ZP for any like prime factor P of N. But there are other cases where we don't know yet. And there's certain things like if you're representable over Z2, you're not necessarily representable over Z4. One example of that is like the Phantom Matroid. So yeah, sometimes.
Yeah, thank you. Thank you for.
Yeah.
Very interesting. Could you go back to where you showed all of the previous results on matrix minor, or not all of some previous results on
Yeah.
excluded minors?
Yeah.
Okay. It was U24, not U23. I was wondering if,
Yes.
you know, somehow we had found two weird bijections, but no, different uniform matroids.
Yeah, U23 is a graphic matroid, which means it's representable over every field.
Sure. Okay.
So it would have to be representable. Yeah.
Right. Okay. That's my only question.
Related to that, could you possibly elaborate on the differences between U23 and U24? Like it seems very odd that one of them controls representation over non-abelian groups, but the other one only seems to control representations over binary fields, etc.
Yeah, so one way you can think about that a little bit, I mean, I can explain U24 more, but U23 is a minor of U24. So if U23 is not representable, then U24 won't be either. But U24 is, so our uniform matroid, let me go back to where, oh, so many. Okay, so here where I was looking at U23, U24 is the matroid I get where I keep the first part of my rank function the same. I say that the card, any subset of size 1 or 2 is going to have rank that cardinality. And then actually I keep this entire thing the same. And then everything else is just going to have rank 2. So my 3 element set has rank 2 and my 4 element rank has set 2. So you could try to, I think it's easier for me to think about like, why is it not a graphic matroid? So U24 also, we can't draw it as a graph. And so my best suggestion for you is try drawing it and you'll figure out pretty soon sort of why you get stuck.
Thank you. Yeah.
Yeah.
And I saw that Kyle was trying to get a question in. Let's see if we can get one more question before the recording stops.
Thank you. So this may be a strange question, but like, does this construction allow you to get a nice like representation of the group? Like what do you mean, like a rep theory like representation?
Yeah, no, that's a good
Like-
question. So it turns out that if we look at the dual object, so if we take a dual of anything represented by a group, our sort of dual representation is no longer the group itself. It's related to the representations of the group. It's something like the permutation represent, or like the action of G on the permutation representation, or of the cosets of the group.
Okay.
Yeah,
okay,
so it very directly gives you some information about the representation.
right. Okay, but not on this thing, but rather on the dual. Is what you're saying.
Yeah.
Okay, that's pretty cool then. Thank you.
Okay, if you have more questions, feel free to try to track down Prairie outside of this. But for now, let's thank Prairie one more time.